So welcome to lecture 14 of MCS 507, a course in mathematical, statistical, and scientific software. So the plan for today is to look into programming GPUs from within Python. So this is the third lecture on parallel computing in this week. We started out with what is provided in Python, so the multiprocessing module and the threading module on Monday. On Wednesday, we looked into MPI for Pi, and today we will look into two packages, PyOpenCL, PyCUDA, and also I will say very briefly mention CuPy. So what's the purpose of these packages, or what's the purpose in this course here for these packages? Well, just like MPI for Pi allows you to start thinking with message passing, the packages that we will see today will allow you to start thinking about data parallelism, how graphics processing units can be used. So we will see two packages, PyOpenCL and PyCUDA, because so far there are two standards for GPU computing. Most likely there are many more standards, but these are the two standards that we will be focusing on. So, but first of all, what are GPUs and what is general purpose GPU computing? Well, there is the graphics processor that has become faster than the general CPUs. So the processing speed of one core, the peak performance is around 1 billion floating point operations per second. For a GPU, certainly a high-end GPU, that peak performance rises to 1 teraflop. But already, if one uses one GPU, then a speed up of a factor 10 is actually can be expected already without doing much specific work because of the increased memory bandwidth. Many applications, by the way, are memory intensive, are memory bound and not really compute bound. The other point of GPUs is that everybody can actually now do massively parallel computing. So, and teraflop performance 20 years ago was still in the range of an entry level supercomputer. Also the other and the last part here, this is not an applied math class, but there are actual applications for hardware accelerators. Okay, so here are the three high-end GPUs I have experience with. So the Kepler, the Pascal, and the Volta, as they are named, they're all three from NVIDIA. And here you see the massively parallel aspect of it. So when we were doing multi-threading, the number of threads should be about the number of cores, and sometimes one indeed may have a multi-core where it's 64 is a very decent good multi-core computer, but 64 in some sense pales into comparison with the thousands of CUDA cores that we are having on an accelerator. On top of that, so the massively parallel scheduling means that in order to keep the GPU occupied, one must schedule sufficiently many threads, often a multiple of the available cores. So you see the evolution. So the peak performance with Kepler, and Kepler is now almost 10 years old, was 1 teraflop. Although it was kind of hard to get this teraflop because the number of streaming multiprocessors was rather limited. So one needed to schedule everything in multiples of 192, which is kind of inconvenient. Pascal got 5 teraflops. The Volta has 7.9 teraflops, and the latest, the current one, actually Ampere, exceeds that. And also there are tensor cores that are coming up now. I was mentioning the peak memory bandwidth. You see it went from 208 gigabyte per second to 870 gigabyte per second peak bandwidth. Massively parallel computing. And how does one run this? With message passing, we had a single program, multiple data model. Here we have single instruction, multiple data. So the level of parallelism is a lot finer. In the other the other way then that makes this work is the data parallelism module, where streaming multiprocessor dictate what blocks of threads are going to execute. So when one designs these massively parallel codes, one thinks of a finest granularity, and one is going to map functions onto the GPU. So we will define functions where every thread computes on one data element. So think about how graphics processors work. One has a matrix of pixels, and the pixel computations for rendering an image or improving an image are here. The programming model actually follows a little bit that level of work. So we will do kernel launches, as they say. A kernel is operating on a grid of blocks, and every block has at least one thread. So one can view one block as being executed by one core, by one streaming multiprocessor. One can run multiple different functions that are being scheduled on different streaming multiprocessors. Okay, first package, or first language. So there is open computing language, which is an open standard for parallel programming. So it is a standard in the sense that it provides a very wide open. It runs on. It pretends to do also it not only pretends, but it covers also the multi-core computing, so the multi-threaded computing, in addition to the GPU computing. Very much related, and I often confused in the early beginning the OpenCL with the OpenGL. So there is a standard also for graphics cards, for high performance graphics. So why is this standard important? Well, there is in essence NVIDIA and then everybody else. So the OpenCL is everybody else. So OpenCL used to be very well supported on NVIDIA graphics cards. So there was a software development kit that came with every NVIDIA GPU that one bought. This practice has unfortunately been abandoned. Um, but OpenCL actually works quite well on, not so surprisingly, on MacBooks, given that OpenCL was initiated by Apple. So there is I have a server called Pascal for the name of the graphics cards, and OpenCL is also installed there. Okay, what is the advantage then of using PyOpenCL? Well, OpenCL itself, because it's such a general standard, is a lot more complicated to program. Not so complicated if you're used to it, but there is a lot of what they call boilerplate code. So one has to stage the data, one has to define the data layout first on the CPU. So the CPU is called the host and the GPU is called the device. And then one has to give explicit instructions for sending the data. So PyOpenCL kind of makes this a lot of boilerplate code, makes it a lot more smaller, a lot less tedious to deal with. The other, so then you can focus on the kernel. PyOpenCL also supports NumPy, so one can work with NumPy arrays. So unlike MPI for Pi, where we could send and receive any Python type, here actually the data structures are much more limited because of the data parallelism. So one immediately has to think at a much finer instruction level parallelism. That is not so much to the technology. Well, it is because of the type of parallelism, the hardware acceleration with massively parallel model. Okay, so I will indicate that there are many tools. So here is the PyOpenCL that is running on that Pascal machine, where here you see that when we check for the platforms and the devices, we actually see the NVIDIA P100. There is also one regular graphics card that is attached to this computer. Okay, so that's to check that actually the PyOpenCL installation was working correctly. And then let's check the matrix multiplication. So the point of this presentation here, of this lecture, is not to do really high performance computing, although we will get to it in the exercises, but to test how to define a kernel. The standard kernel is the matrix multiplication. And here we see this executed on two integer matrices. Actually, they are true-false matrices. This allows them to verify the correctness. So what we are trying to do here is to indicate how you can use the GPU for matrix multiplication. Matrix multiplication, by the way, is a very fundamentally important construction in linear algebra, but therefore also in scientific computing. The textbook, one of the textbooks that we are using in supercomputing class for GPUs spends a couple of chapters, so entire chapters on this matrix multiplication problem. Here we start the script. So we have to import PyOpenCL. We will use the data type that comes from NumPy. And the graphics card that I was using here, I think it might have been in a laptop, and the graphics card was not supporting 64-bit arithmetic. So I was going with the 32-bit floating point arithmetic. Most modern graphics cards do support 64-bit precision. Okay, so that's the beginning. We have the matrix dimensions, so we will have a 3 by 4 matrix and then a 4 by 5 matrix. So A is 3 by 4, so there will be 12 numbers for A and 20 numbers for B, and then C will be a 3 by 5 matrix. So one sees these definitions here. Notice that the matrices we will here generate random integers, so random bits essentially. So between 0 and 1, not 2, so bounded by 2, or 0, 1 for the integers. Then, so we make the matrices will be integers, but then we change the type. So in NumPy, we change the type from an integer matrix to a 32-bit float matrix. So this takes care of the typing. It's also good that we started out in this course with NumPy. So NumPy supports types. We also saw that in the MPI for Pi lecture. So in a way, types explicitly indicated are actually now really a requirement. Also, the data structures in Python, we like lists because they are so versatile, but here actually we really need to use the arrays. Alright, so then here is the boilerplate code. So we will have to, we have our matrices on the device, the A, the B, and the C, but now we have to define the counterparts on the device. And that is done here with these instructions. So you see we have an A underscore buff, a B underscore buff, and then a C underscore buff. So we make the declarations for the queues. So this is something that one always needs to do when one needs to think that we have data that lives both on the device and both on the host. Okay, and now comes the hardest part, the definition of the kernel to do the matrix multiplication. And here, what actually happens is that there is a compilation that happens. So Python is interpreted, whereas everything that happens on the GPU, that gets executed on the GPU, actually is compiled. So how does this happen? Well, when we run the program, there is here a build that is being done. So we had to build earlier with the setup tools where code was generated for an extension module. Here a similar feature is passed through. So through the CL to the computing language, we define a program within the context, the defined context, and we are multiplying the matrices A with B. The global underscore underscore indicates that the matrices reside in the global memory of the graphics card. So that means that every thread has access to the data. We also pass the N, M, and P as short integers, unsigned, the dimensions. So now every thread in this kernel has a unique identification number. So we get the global identification number. So we are going to compute 15 numbers. So we can launch here 15 threads. So that's important too. So matrix-matrix multiplication is very well suited for graphics processing computing because so much can be done independently. Okay, the matrices are actually stored C-wise as one long array. So we have to compute the row and the column index of the matrix C. So here what is happening is that the global identification number of the thread will indeed determine the row and the column index. So here you see the computation of the row index and the column index in the C matrix. That's computed here. So this is stored in two registers. And then we have two pointers, to address locations of the data. So this is C. So pointers are references in Python. So we will go over all the rows of over one row of A, and we will jump column by column. So we actually have the number of rows, and I'm sorry, so we will not jump. So we will go in one row. So we compute the beginning position in A. So that's the row number times the number of elements on a row. So here this is most likely very inconvenient that I do not have a drawing here. So remember the numbers, we had 3, 4, 5. So what we are looking at is the matrix A has 3 rows and 1, 2, 3, 4 columns. So these are the elements now. So this is the first row. Then we had 4 rows and 5 columns. So we had 3, 4, 5. So 4 rows here, and here we had 1, 2, 3, 4, 5 columns. So if we are going to compute the index 1, 2, so this is then in the matrix C, then we have to run over all the rows, all the entries here in red on this row 1, and then on column 2. See the dots line up. We have 4 red dots here, 4 red dots there. Now the matrices are stored row-wise in one long row. So this is a logical representation. But you see, if we store the matrices row-wise, row by row, then we can go to the next element just by adding 1 to the pointer. So that's happening with the PA++. So in the loop, we are going to go each time 1 up here, But here each time we have to jump. So we have to jump. The pointer arithmetic starts here based on the 2. So you see the beginning position of B starts with the column index. That's easy, but then each time we make a jump in the loop, we are going to recompute essentially the position of B. So it's not done with an explicit addition, although here you see we have the K times P. Okay, so, but that's essentially the algorithm in C for computing one element in the in the um, in the matrix product. Now, typically, the matrix product, you go over all the elements of C, and then you have another loop to go over the row of the first and the column of the second. So here you see only one loop. There is one explicit loop sitting here that is to compute one element. The other two loops are being realized by the kernel launchers. So theoretically, one has a potential speed up of n square. So the matrix multiplication, that is in general a cubic operation, cubic in the dimensions, comes now linear. So you see the massive reduction in the costs. So we can expect very huge speed ups. Alright, so this took a long time to explain, but that's the most complicated aspect, and that is related to the parallel organization of the matrix multiplication. Now, this is not the way to do it, but that's the simplest way to do it. The actual algorithms, but this then goes into a supercomputing class, will actually use tiling. And we will use the shared memories in the GPUs. This is here hidden from view. So in this simple illustration, we want to verify that we can define from within Python and without having to compile anything explicitly. So the compiling and the linking on a GPU can also be quite involved. Also, PyOpenCL takes care of this. Okay, so then there is also so this is quite done, probably still in Python 2. And here I just give this demonstration. So this was done on the software development kit on the earlier releases of the NVIDIA graphics cards. So this gives the number of floating points per second, and does some tests. So you see the CPU time, the GPU speed up was done on a laptop, not on a high end. So the GPU is still here slower than the CPU. Okay, PyCUDA. Okay, so I could have given this script earlier. Again, what is the big idea here is that you as a programmer can mainly focus on developing your idea in a scripting environment. So there is a green box, and there is kind of here reddish looking box. So the GPU code, the GPU compiler, GPU binary, GPU run to the result, this entire level here is actually taken care by this PyCUDA, but also PyOpenCL. So these are code generators. So next week we will see Cython. Cython is another way to generate and compile and run C code without having to go to the lower level of actual compiling, linking, and running. Okay, PyCUDA. So getting it installed, of course, you must now have an NVIDIA GPU and also have the drivers installed. One can check whether everything works by the instructions on this slide here. So the point again is that this is always interactive parallel computing. Okay, I executed this also on a Windows laptop. So just to indicate that this is supercomputing that has gotten very personal. If you have a high-end laptop with a good graphics card, then you can get a lot of work done. So this card, by the way, is about, in my experience, about almost as fast and certainly easier to use than the earliest Kepler cards. So one can get already very good performance out of a card like this. All right, matrix multiplication again. So we do the same thing. So the Python script executes, shows the matrices and the graphics card. So we have now a 3x4 and a 4x5 again. So the graphics card computes 15 numbers. And here this is testing whether the installation works. And again, the main purpose of this lecture is to have a kind of a taste of what GPU computing is like. So it is hardware, it is acceleration, it is the helping of the CPU. One looks at the portions that in any computationally intensive computation that can be accelerated. So one very seldomly starts implementing from scratch on a GPU. One must always have a program running on the CPU. Okay, here is the setup. So we have the dimensions 3, 4, 5 declared now explicitly as NumPy 32-bit integers. Here I generated my matrices as n, m matrices. So in the previous PyOpenCL, I had n times m, and then I had m times p. So in this portion of the code, we define, we import all the modules that we need, all the packages that we need, and we define the data on the host. We define our input matrices, random matrices, and we initialize the resulting matrix. Okay, then there is the allocation. So perhaps I should have presented PyCUDA first before doing PyOpenCL, but at this stage we are perhaps no longer that fresh. We took the hardest code first. Perhaps if you remember, the OpenCL code was actually a lot more complicated. We needed more lines of code. Here we allocate memory for the corresponding matrices on the GPU, and then we do the memory copy host to device. So the H2D means host to device. So the host is the second argument. So the data on the host is called A and B. The data on the device is called A underscore GPU, B underscore GPU. This is something that one always needs to do. So the code is a little bit shorter, The main advantage of PyCUDA here is that the allocations with NumPy go a lot nicer than they would be with C. And again, there is no compilation at this stage. Okay, so here we have the C code again. It is written in in a slightly different format, although here we are also exploiting the fact that matrices in C are stored row-wise. So you see the pointer arithmetic that is happening again. So we are now explicitly computing the thread indices. So the syntax is that we can launch our blocks of threads in a two-dimensional structure. So the PyOpenCL code was a one-dimensional launch. Here we will have a two-dimensional launch. So there is an index, a first index and a second index. So you have the .x and the .y. So our threads, so we have 15 numbers to compute. The 15 numbers are arranged in 3 rows, 5 columns. So the threads have a double index name. So they have the one that is going to compute 1, 2 will actually have that name. So the thread index.x will be 1, the thread index.y will be 2. And we have a global index. So that global index is needed to access the data. Okay, so here it's actually a little bit simpler. So the syntax is simplified. The global is not really there. And we have the loop with the explicit bracketing now. So we don't do the pointer arithmetic. So the style of writing C codes is here a little bit clearer. So this is not because we're using PyCUDA, it's just showing that in C there are different ways of coding things up. Alright, then we have the launch of the kernel. So with OpenCL I probably was not too careful about this. Let me do this here. So we will define the function. The function takes on arguments, the dimensions, and then the pointers to the data. So we have the two matrices A and B for the input, and then the result matrix C underscore GPU. We will launch here in this example 15 threads arranged in rows and columns. So you see we have also we could also have had a .z thread index. So they allow for a three-dimensional block structure. The gridding is one-dimensional, so there is a six-dimensional structure of launching threads that can be done. So the blocks can be arranged in grids, and these grids can be two-dimensional. Here we are essentially only launching one block. This is a very small matrix also, by the way. Okay, very important, we had the memory copy host to device. We have to end, before we can do the print, we have to do the memory copy device to host. So before we can print the data. So this is interactive GPU computing. However, you can't really print within the functions, within the kernel functions that are executed by the GPU. So that's also one motivation to keep the kernel really, really short. So that's a mistake that often is made, to write very, very long kernels. And these are then extremely hard to debug, but also for the system at the instruction level, very difficult to execute at the best way. Okay, so that is the first introduction into PyCUDA. Then there is also CuPy, which is more recent than PyOpenCL and PyCUDA. Um, it is more on top of it's more tied to NumPy. It's geared towards CUDA, but there are also efforts underway to make it run on other GPUs. And essentially, it also takes care of the compilation and the execution. Um, so the first time you run it, you have to account for all the compilation, but the second time, it will be executing a lot faster. Okay, so that's kind of the main point. We can develop GPU kernels already in Python, so stay as much as possible within the scripting environment. However, one needs to understand how GPUs work, and one also needs to understand how matrices are represented internally. So there is this C syntax that is kind of unavoidable here. So the exercises are rather open-ended for this lecture. So this could turn into a second project should you be interested in this course to explore GPU computing. If not, then this was a first introduction, and I hope that it kind of gives you a feeling of how, as a programmer and as a software developer, you could start developing functions that run on the GPU. Okay, thank you for your attention.